All right, so this is the video lecture for Chapter 7. We're going to be starting talking about the solar system. So we are done with all of the stuff on light and telescopes and all the background material. We're ready to get into the meat of the class, which is going to start with solar system, and then we kind of expand out from there. We'll talk about the sun later, and then we'll talk about other stars and then galaxies and so on. But today, this lecture is all about the solar system. And this picture here illustrates what the sizes of the objects in our solar system are to scale. And when we think about our solar system, we tend to want to think about them in groups. We tend to want to think about like bulk properties instead of just looking at the individual objects and what their properties are. And I will do that to some extent. I'll talk about the individual planets and talk about their details, but I'll do that with the mindset that we want to understand how they're similar to other planets and why they would be different from the other planets. And this is a part of astronomy that we refer to as comparative planetology, where we want to understand planetary types rather than understand like the individual details of the planets. Okay. To do that, we're going to be interested in looking first at the general characteristics of the solar system. And we want to be able to explain why these general characteristics of the solar system exist. And this helps us understand the planetary types. So the first point here is the solar system is in the shape of a disk. And we'll talk a little bit about this today, and we're going to get into this more when we talk about stars. But there's a good reason for this. It's not a coincidence that all the planets in the solar system lie on the same plane. It's not a coincidence that they all orbit the sun in the same direction and that they rotate in a very similar way. And there's a reason for this, and it has to do with the fact that our sun and the planets form together, which is not an idea that had always been believed in astronomy. In fact, one of the ideas a very long time ago in very early astronomy in the 20th century was that maybe the sun formed first, or maybe the sun has always been around, and then something caused the planets to be formed. Maybe they formed out of the sun or something like that. So, but we have a theory now. We call it the solar nebula theory that discusses how the planets and the sun would form together. When we also look at our solar system, we see that there are planetary types. The four inner planets, and I'll go back to the picture here. If you see the four inner planets, which are in the bottom left here, they have a lot of characteristics that are very similar to each other. Mercury, Venus, Earth, and Mars are all called the terrestrial planets. And it's because they have very similar characteristics to each other. They're very similar to Earth in a lot of ways. The outer four planets are what we call the gas giants, or the Jovian planets. That is Jupiter, Saturn, Uranus, and Neptune. Same deal. Very similar characteristics to each other. And dramatic differences from the terrestrial planets. And we're going to be very interested in understanding why that it exists. When we look at the outer planets, they have a very elaborate ring systems. It's not just Saturn that has rings. Jupiter has rings, and so does Uranus and Neptune. And the outer planets have a lot of satellites, have a lot of moons, where the inner planets don't. The inner planets do not have satellites, very few, if any, actually, and no ring system to speak of. We have a lot of leftover things. We call it space debris. We have a lot of stuff that in the solar system that for whatever reason has not found its way into the sun or found its way as to be one of the planets. These are asteroids, comets, and meteoroids, I should say. And we're going to be interested in understanding why those exist. And then also when we look at all of these things, the sun, the planets, any of the space debris, careful study of these things all point towards a common age, that they all have a very similar age, and that age is 4.6 billion years old. So let's first start off with the solar nebula theory. This is something we're going to talk about in two different parts. When we talk about the formation of stars, we're going to revisit this, but it's relevant now because it's the sort of the story of how the planets formed. And the basic idea behind the solar nebula theory is that planets and stars form together out of the same material. What happens is we start off with a very large, cold, dark interstellar cloud. Something triggers the cloud to experience a contraction. It starts to shrink in size, which becomes a runaway process. it shrinks further and further. It starts to heat up. It starts to flatten into a disk and spin more rapidly. Most of the material, it's going to find its way into the sun, but some of it stays out into the disk. And as that disk starts to cool, it starts to condense. And we see chunks of matter start to form out of that disk. And as they go around the sun, they start to sweep up material. And this is what we see as planets basically growing as they go around this disk. And we have a lot of observations, mostly due to Hubble, of nearby young stars that still show evidence of this stuff. So there's a lot of evidence for the solar nebula theory, enough now that we're firmly convinced that this is how planets form. They form with stars. It's a process called accretion, where all the material is slowly swept up and added to planets, and they grow in size until we have what we see today as our solar system. So that's the basic idea behind the solar nebula theory. Now, that in mind, a lot of things about the properties of our solar system make sense. The disk shape makes sense. The common motion of things makes sense. If everything formed out of this disk, then it makes sense that everything goes around the sun the same way, because it's simply the way the disk moved in the early solar system. So basically all of the properties, the motion properties that we see for the planets, are simply inherited. They're inherited from the disk that they formed out of. So that helps us understand a lot about the process by which they form. And then we look at other aspects. If you're close to the sun in that disk, well, the sun is going to have a stronger gravitational influence. So it's going to be harder to, one, gather a lot of mass. The sun's going to take a lot of it. So we see that the inner planets don't have a lot of mass, and the outer planets do. We see that the inner planets, the mass that is there, is very dense, as opposed to the outer planets that have a lot of light gases. And that makes sense. That's a centrifuge effect. That as the spinning disk happens, things tend to sink towards the center that are heavier, and lighter things stay fuller out. Temperatures. The temperature of the inner planets are much higher than the outer planets, and that makes sense from this standpoint as well. If you're close to the sun, things are hotter. So, when we think about the way our solar system is, we think about, okay, well, how did things start and how did things progress? And when we think about distance, there's the sun's influence, there's temperatures, and all those kinds of things. And so that's what we want to keep in mind. When we look at the properties of all these planets that we're going to look at, we want to understand these properties in the terms of the solar nebula theory. Okay. So I have some questions here, a couple questions that helps us, see how we use the solar nebula theory to understand, some of the properties that we see. So anyway, the question here is, the solar nebula theory successfully predicts all but one of the following. Which one does the theory not predict? So think about that for a moment. And here the answer is going to be D. Equal number of terrestrial and Jovian planets. There's no reason why there should be 4 and 4. There certainly could be a lot more terrestrial, less Jovian. There's nothing about the solar nebula theory itself that says how many there would be. But the other ones make sense. For A, planets orbit the sun in nearly circular orbits in a flattened disk. Well, okay, that makes a lot of sense with the solar nebula theory, because the swirling ball of gas flattens into a disk, so we expect that. Compositional differences between the terrestrial and Jovian planets. The inner planets are heavier, rocky. The outer planets are lighter, made up of a lot of gases. Again, that's that centrifuge effect I talked about. Craters in the moon. Not all of the material will be swept out by the planets. We certainly expect there's a lot of leftover pieces, and those leftover pieces are the asteroids and the comets and the meteors. And what happens is, over time, they wander the solar system, and they will eventually hit things. And when you look at solid surfaces, we see cratering. When you look at any kind of asteroid, lots of cratering. So there's a lot of bombardments that take place, and that is consistent with the idea that objects form, things get swept up, but not everything gets swept up. It takes time for that to happen. So C and E make a lot of sense in terms of the bombardment aspect, having leftover pieces that need to be swept up. So now, this picture here is illustrating the relative motion of things in the solar system. And we talked a bit about this already. But when you look at the planets, every planet orbits the sun prograde. Counterclockwise, every planet does that. When we look at the rotation of planets, every planet rotates Same thing, counterclockwise, prograde, except for two things. There are two exceptions. Venus rotates backwards, and Uranus has a axis of rotation that's tilted on its side, so it kind of rolls through the solar system. You should think about it like that. And this is not incredibly surprising. We would expect, because of the bombardment aspect I talked about earlier, that there's alterations. There's a first order effect, which is the solar nebula theory, but then there's an aftermath. There's things that happen afterwards. And for Venus in particular, and I'll show you the pictures of this later, it looks like something probably hit Venus in the recent past. Recent past meaning maybe a few 100 million years ago. Something looks like it may have hit Venus, it melted the surface, and it might have caused Venus to flip over. And that's why it appears to rotate backwards, because it actually rotated prograde, and then it flipped over. Same thing with Uranus. Very possibly something hit Uranus, tipped it over on its side. If you look at the rotation of all the planets, none of them are perfectly straight up. Everything has a tilt to some extent to it. And so we expect that to be an aftermath thing. In terms of inclinations, everything is pretty much in the plane of the solar system. The biggest exception is Mercury at 7 degrees tilted with respect to the ecliptic, but there's a reason for that. It's a good reason for it. It has to do with an interaction with the sun that over time tilts the orbit of Mercury. So that's completely expected. But all the other planets are very closely aligned with the disk. So these dynamical properties, again, make a lot of sense with the solar nebula theory. All right, so question here about why do we find some exceptions to the general rules and patterns of the planets? Right, let's read over these. And the answer here is A. Most of the exceptions are the result of giant impacts or close gravitational encounters. This is the aftermath that I talked about. Things form a certain way. Afterwards, there are events and accidents and things that happen. If you go over the other options, we can see why they're wrong. B says the exceptions exist because even though our theory is correct as possible, nature never follows rules precisely. Well, that's completely false. In fact, science couldn't exist if that were to be true. Nature absolutely follows rules precisely. That's the whole reason why we can study this stuff, predictability. So B is completely false. C, our theory is not quite correct because it cannot explain these exceptions. Well, that's not how theories work. Theories are designed to accomplish a certain task. They're not meant to be all-encompassing. They're meant to explain a particular behavior, and of course there's little exceptions that occur. For example, Kepler's laws. Kepler's laws work excellently. They explain the motion of planets almost perfectly, but one thing that Kepler's laws does not do is it does not account for the fact that planets can interact with each other. It only accounts for the fact that the sun interacts with the planets. And those little tiny interactions that happen between planets can throw off the orbits a little tiny bit. And it doesn't mean the theory is wrong. It just doesn't. It means the theory is not that all-encompassing. So it's not necessary. D, the exceptions probably represent objects that formed recently rather than later in the history of the solar system. Well, I kind of explained this in the beginning. We don't believe that to be the case. We don't see evidence for that. When we look at all things in the solar system, they all point towards a common age of 4.6 billion years. So D could be right, but we just don't see evidence for that. Okay. All right. So I mentioned the two types of planets. We organize the terrestrial planets into Mercury, Venus, Earth, Mars. We kind of throw the moon into that because they're so similar. The moon is so similar to the terrestrial planets, so we're just going to throw that in there. And then Jovian planets is Jupiter, Saturn, Uranus, Neptune. Again, we're doing comparative planetology. While I will be talking about the individual properties for the planets, we are generally interested in understanding why they're so similar to each other and why these planetary types exist. And to be clear, these are not the only planetary types. The Kepler Space Telescope, something that launched a little less than a decade ago, and it's discovered thousands of other planets. And we've learned that there are definitely other planetary types. We just happen to have two in our solar system, but other solar systems have other type of planets. And that's a discussion we're going to have in a few weeks when we get into extrasolar planets. This is not the only types you can have. But we definitely want to know why we have these types in our solar system, why they're so similar to each other. And so we're going to get into that. Let's start with terrestrial planets. So for terrestrial planets, here are the general characteristics. We have 4 of them. Again, there's no reason why there's 4. There could be more, there could be less. The solar nebula theory doesn't really address the 4, basically. All of these planets are very small in mass relative to like the outer planets, and they're small in size. Earth is the biggest one. Venus is a tad smaller. Mercury and Mars are significantly smaller than the Earth. They all have rocky surfaces. You can land a spacecraft in all of them. They have very weak or non-present atmospheres. Obviously, Earth has an atmosphere, but it's actually considered rather weak compared to the outer planets. Venus has a very thick atmosphere. Mars has an extremely thin atmosphere. Mercury and the Moon, they have basically no atmosphere at all. In terms of moons, Earth obviously has 1. Mars has 2 captured asteroids. We call them moons. We know they're captured asteroids. Mars will lose them in the future. They're not a stable thing. Venus has no moon, and Mercury has no moon. None of these objects have a ring system on them. So that's the general characteristics of what we see for terrestrial planets. So let's go through them. Now this first object here is Mercury. And, if I showed you this picture actually, without telling you it's Mercury, I mean, you might be tempted to say, well, that's the moon. And there's a reason for that. The Mercury and the moon have a very similar appearance to them. They're both very heavily cratered, and they're kind of grayish in appearance. And that's not a coincidence, actually. If you don't have an atmosphere, there's not much that can shape the way the planet looks. If you look at the Earth, what shapes the Earth? Wind, rain, things like that. Well, there's no atmosphere, so Mercury and the moon can't be shaped in that way. What can shape it? Well, impacts. And you look at the moon, the impacts there are extremely old, billions of years old in some cases. And Mercury is the same way. Without an atmosphere, there's really no way to change how you look. The object formed this way. It was initially very hot, so most of the rock that you see is basically like volcanic rock that's never really changed over billions of years. But the cratering is what dominates it. Okay. It's the closest to the sun. It's not the hottest, though, and that's also due to the atmosphere. There's a side that faces the sun that gets extremely hot, and a side that faces away. Mercury does rotate. It's a relatively slow rotator. The rate at which it spins is something like walk-in speed, basically. A slow walk is the rate at which, a slow walk of a human being is the rate at which Mercury spins. And so one side gets incredibly hot, 600-700 Fahrenheit or so, and the other side is horribly cold. Now, what you see in the picture here on the left-hand side is what's called the terminator. That's the day-night line. And in fact, the day-night line, that terminator, is at somewhere along that line is going to be a moderate temperature, like a temperature you'd experience on the Earth, because it gets super hot on the bright side and super cold on the other side. Somewhere in the middle, there's got to be a moderate temperature. So if we were to ever actually go to Mercury, land on it, maybe visit it, we could certainly do that. You'd have to be on the side, though, where the terminator is. And you'd actually have to have something that can move. So there's actually a science fiction story I was reading about traveling to Mars, and the idea is that if you travel to Mars, you'd have to build some kind of space station that can slowly move across the planet, so you will always stay on the terminator. And the point of the story was that space station breaks down, and then they have to find a way to fix it. Otherwise, it's going to rotate into the bright side, and they're all going to burn up and die. So I don't remember the name of that. If I do, I can post that later. But anyway, no moons again. We visited this a couple times. Mariner 10 was a mission way back in the 70s and 80s. And that was the first trip we went there. And then most recently was Messenger. That was an orbiter. It orbited for a while, took lots of pictures, which is the source of this picture here. And then it crashed into the surface. So Mercury is interesting. In fact, while it's pretty bland for the most part, we think there would actually be liquid, not liquid water, but ice near the poles. There's cratering near the poles, and because of the cratering, it's very likely that sunlight doesn't hit the bottom of some of the craters. And so we believe there could be ice in these craters, and we're very interested in that ice because it would be pristine. It would be basically water that has existed for billions of years untouched. And it would be very important to study that because it would be there would be a lot of clues in there to what the early solar system was like, and so we could better understand how some of these terrestrial planets formed. But it's not a high priority to go to Mercury, so I don't know if it's going to happen anytime soon. That's Mercury. Venus. This picture here is a visual wavelength image of Venus. If you see Venus in the sky, this is pretty much what you're seeing here. It's not a typical picture you see of Venus because it's rather bland. Venus is a very thick atmosphere, very thick clouds made up of carbon dioxide and sulfur dioxide, and that gives this kind of like an orangish, almost yellowish kind of appearance to it. And the clouds don't really reveal much. This ends up being the hottest planet in the solar system, and it's because of the atmosphere. Even though it's farther from the sun, there is what's known as the greenhouse effect that occurs, where light can enter through the clouds because the visible wavelength can penetrate atmospheres, hits the ground, heats up the ground re-radiates that energy, and it does it in the infrared. But with all these oxides in the air, these dioxides, the carbon dioxide and sulfur dioxides, they absorb that infrared radiation and it traps it, which is your basic greenhouse effect. And so what would happen is instead of the light just coming in and leaving, it gets trapped and stored. And that builds up the temperature to a temperature of around 900 Fahrenheit in extremely hot temperatures. I mentioned before that Venus is a slow rotator. It rotates backwards, actually. A day on Venus takes about 250 Earth days. And I mentioned that it's likely due to an impact. In fact, this is another picture of Venus taken with radio waves. It's a radar image, basically. And the radar can penetrate through the clouds. So what happens is it bounces off the surface, comes back, and we get some topology. We get like the elevation. We get some of the features on the surface. And so this is a picture you may be more familiar with. Now the color is artificial. It's not meant to be, yellowish orange or whatever, but it's colored that way. And it sort of does look like that when you're on the surface. And there's an image I'll show you in a moment here that shows that. But the Venus doesn't display a lot of cratering. It just actually displays a lot of what appears to be volcanic activity, a lot of volcanic material on the surface, cratering, volcanoes. In fact, one thing of great interest is to investigate whether Venus is still geologically active. We strongly believe that that volcanoes are still erupting on Venus, but it's difficult to see. The way we detect it is you look at the volcanoes and you look for warm gas coming out, which would indicate there's things going on inside. And we detected a little bit of that back about 5 years ago or so in 2014. We visited a few times, mostly orbiters. The Venus Express was a mission that was able to produce this image here. The Russians were the first to go to Venus, actually. And it's a very interesting story, what happened there. In fact, this picture is a picture taken from Venera 9. And it's actually the very first image that was ever taken from the surface of another planet. And you can see it's not a pleasant environment. It's the ground is very it's looks like volcanic. If you've ever been to like a volcanic site, this is kind of very similar appearance, but it's flattened. All the rocks are flattened out because the atmosphere is almost 100 times the atmosphere of the Earth. And so the rocks get flattened out by the atmosphere. The sky, it looks disgusting. It's this gross yellowish, and that's mostly due to the sulfur dioxide. We believe it rains sulfuric acid because of the atmosphere in here. It's interesting. This picture is interesting, though. So to give you some of the history here, this is called Venera 9 because there were 8 other Veneras that didn't make it. What happened is Americans go to the moon, right? So there's a space race with the Russians in the 60s, and in the late 50s, early 60s, there's this big competition, mostly politically driven, to get to exert our dominance over space. And at this point, the Americans made it to the moon. So that was a big step. Russians did a lot of first satellite in space, got the first person in the space, and so on. I think the Russians were also the first to get a satellite up and around the moon. They actually took a picture of the moon on the other side for the first time, but we made it to the moon, put people on there. So after that happened, the question is like, well, okay, what's next? And so then what's next is let's go to a planet. And so Americans chose Mars, Russians chose Venus, and they were they kind of very hastily prepared their missions to get there. Several of the Venera missions didn't make it to Venus. I mean, they either completely missed the planet or they broke on the way or something. A couple of the missions actually made it into the atmosphere, but they didn't realize how hot it was and what the atmospheric pressure was. And so a couple of the missions just were crushed, basically, just destroyed upon reaching there. Venera 9 made it, landed, only lasted a few hours, then it was destroyed by the atmosphere. But they were able to take these two pictures here. And so we actually get a glimpse of what the planet's like being on the ground there. Now, if you look at the picture on the right, there's this little piece on the ground in front of the instruments here. That's a lens cap. And what the story is here is there was a lens cap placed on the camera, and the lens cap was designed obviously to protect the camera so nothing happened to it on the way to Venus. The problem is that when it landed, the lens cap was supposed to be knocked off by some instrument so they could take pictures, but before that could happen, it just melted off. And so it just melted, and then it falls on the ground, and it falls where you see in this picture. But the problem with that is that is exactly where another instrument was supposed to reach out and dig into the sand so they can test the properties of the soil that's there, but it just dug into that melted lens cap, so they weren't able to get any decent data there. It's the only attempt anybody on Earth has made to go to Venus. We don't have plans to go back to Venus because it's not a nice environment at all. We'd love to study it more, but it's hostile. It's very, very difficult to do things on the surface. I mean, maybe in the future we can develop a spacecraft that can navigate this a little bit more easily. It'd be interesting, but for now, it's very challenging to do that. Right. Well, I'm not going to talk about the Earth because you live on the Earth. Just look around you. That's the Earth. A couple more pictures of Venus here, I guess. Mount Mons is one of the largest volcanoes on Venus. I mean, the reason for me showing you these pictures is just, this place is awful. I mean, this picture on the bottom right looks like something out of like Mordor from Middle Earth. It just looks like something that, Frodo and Sam is walking through on their way to to throw the ring away. They're just nasty environments. These are cratering, likely places where material is welled up from inside, old volcanoes or things like that. So, all right, let's get to Mars here. Now, Mars is very interesting because it's most similar to the Earth in terms of how it looks, some of its properties. Mars has a day cycle that's very similar to the Earth. It's only about a half an hour longer. Has an axial tilt very similar to the Earth. Remember, the Earth is 23.5 degrees. The axial tilt of Mars is 25.2. So what that means for the axial tilt being very close to the Earth is that it experiences seasons, much in the way that we do. Now, Mars has a longer yearly cycle, so their seasons are like around 7 months or so instead of our 3 months. But we're interested in Mars because it's a place that's probably most similar to the Earth, meaning we can possibly go there. Now, it's not a place you can walk on, obviously. Very weak atmosphere, no oxygen, mostly made of CO2, but it's very, very weak. It has some amazing geology on it. What's labeled in the picture here is Olympus Mons. Olympus Mons is a gigantic volcano. It's 3 times the size of Mount Everest in terms of height, and it's about the size of the country of France. It's absolutely enormous. Valles Marineris is like a giant canyon. Now, the Olympus Mons, and there's actually 3 other large volcanoes in between Valles Marineris and Olympus Mons that are responsible for creating Valles Marineris. Basically, what happened is these volcanoes popped up, and it kind of pulled the surface apart. So Valles Marineris is like a giant fissure, basically, and it's an enormous canyon. I mean, To give you a sense, if you can see in the picture here, the extent, from left to right of Valles Marineris is about the extent of the United States. It's about 3,000 miles across. And at its deepest, it goes all the way down like 6 miles. So, I mean, if you think about the Grand Canyon, if you've ever seen that, it's a joke compared to Valles Marineris. Valles Marineris is extreme in terms of its canyons. It's been the most visited planet. Lots of rovers, lots of orbiters, and we hope to go there one day. It's very challenging, but it would be nice to. You see this picture here? I mean, this looks like somewhere in the Alab Valley, actually. But this was taken with one of the rovers. In fact, if you've ever seen The Martian, a lot of the backdrops in The Martian are actual pictures from rovers. So that's kind of neat. If you haven't seen The Martian, you should. It's one of those rare science movies that does a really good job of explaining what Mars is like, or just science in general. So it's a good one. But yeah, a lot of the information and pictures in The Martian are real. But I mean, it's the pictures deceiving though. I mean, while it looks like a place we can visit and it's nice, it's the sand is very fine. It would be toxic to humans to be around because you'd breathe it in. It would be very bad. It's extremely cold. No oxygen, so you'd have to have some spacesuit there. So, but yeah, this is a great picture too. This is again, this just illustrates how similar Mars is. And we can build space stations there. We can establish. Mars has lower gravity, about 1/3 the gravity of the Earth, and as a result, it has very elaborate caves inside. And so, what we hope is, explore these caves. Very likely, there's liquid water down in these caves. We think there's probably lakes and rivers of liquid water, and very well there could be life actually down there as a result of that. In fact, we've detected. I think I mentioned in the slide back here, small amounts of methane. Methane is typically a byproduct of life. A lot of bacteria release methane as part of their biological processes. And methane is not easy to retain. I mean, if methane's out in the atmosphere, it should escape in space. And the fact that we detect it means there's something actively either producing it or releasing it, and that could be life. So we are very interested in understanding what that's all about. But the plans now are hopefully, in the next decade or so we can get there, but it's going to be very challenging to go. It's very likely a lot of tragedy is going to happen along the way. It's going to be a lot of hardships, but it's very important because this is going to be a big step in living other places. We can't live on the Earth forever. If things go decently here, population grows, resources dwindle. Earth can only support so many people, so we have to really start thinking about living other places, living in extreme environments, and Mars is the good first stop for that. So it's actually extremely important that we get there, and we get there soon. We have to start learning how to live in other places, and Mars is the first stop. All right, so now that you saw all that stuff, go ahead and try to answer this question. Which of the following is not a common characteristic of terrestrial planets? The answer here is B. They do not have large extended atmospheres. That's actually a property of the Jovian planets, but they do have rocky surfaces, small sizes, and very few or no moons. All right, so let's move on to the outer planets. The Jovian planets, we call them gas giants, we call them Jovian planets. Very similar objects to each other. I have listed some of their common properties here. They're big. They're really big, not in terms of mass and size. And one of the reasons for that is because they have a lot of gas on them. These objects are made up with a lot of hydrogen and helium. These are very light, very fundamental gases that don't exist in the inner solar system because they're so light, they're so small, that they're very easy to heat up and have escape. So if you release a helium balloon into, the helium out of a helium balloon into our atmosphere on Earth, that stuff eventually gets out of the atmosphere, goes straight up, out, and then probably will become part of Jupiter in the future. It'll go out into the space, the sunlight will push that gas to the outer solar system, and most likely Jupiter will, as it goes around the sun in its roughly decade cycle, will sweep it up. And that will obviously contribute to these objects growing in size when they sweep up all this material. But yeah, huge, large, extended atmospheres, a lot of gas. If you dig down deep enough, though, there is liquid initially, mostly metallic hydrogen. It's like liquid hydrogen. And if you go really far down, you get to rocky stuff. In fact, the core of Jupiter is like as a mass that's mostly made of a lot of metals, and that's like 3 to 5 times the size of the Earth or so. And so, I mean, not size, mass of the Earth. It's fairly similar in size, actually. Jupiter's only 10 times larger than the Earth, actually. So, but they all got rings. You see Saturn with its rings. Rings are a recent event, we believe, and they will go away in the near future. Maybe in a few 100,000 years, they'll be gone. What likely happened is something got close to Saturn, and Saturn broke it apart, and all the pieces got just kind of flattened down to this disk that we see today. But we know in the future that will be gone. And very likely Jupiter or the other planets can develop their own ring systems just like Saturn. It's just we happen to be around at a time where Saturn has rings and nothing else has obvious visible rings. But Jupiter has visible rings, and so does Neptune and Uranus. Definitely. All right, so Jupiter is the biggest planet in the solar system. And this picture here was taken with Galileo. That was a mission in the 90s that was sent out there. Now, Jupiter, these outer planets have not been visited as much as the inner planets because they're so far away. Jupiter's been visited by 6 things. Basically 6 things. There's been some flybys of other stuff, but Pioneer 10, 11, Voyager 1 and 2, these were missions in the 70s and 80s. Galileo was very recent in the 90s, and Juno was a spacecraft that's there now. It was launched a little while ago. It got there maybe a couple of years ago or so. And most of the images you see of Jupiter now, though, come from Juno. And so not visited by much, some flybys. The mission that went to Pluto flew by Jupiter and took some pictures. But it is the biggest planet. It does not have a solid surface, though. None of the Jovian planets do. It's an atmosphere. If you enter the atmosphere, it's kind of gets thicker and then thicker and thicker. And then as you get deeper down, at some point, it just turns into liquid. No clear transition, though. The atmosphere is mostly hydrogen and helium. There's trace amounts of other things, which is why it has its colors. The kind of brownish colors come a lot, mostly from ammonia and hydrogen sulfide. Some bluish colors come from methane. And you can see the atmosphere is elaborate, right? Just it's beautiful, and it just has all these swirling effects in it. And there's a good reason for that, actually. Turbulence is what it is. Inside Jupiter, even though Jupiter is very old, we're talking about 4.5 billion years old, there's still some internal heat in Jupiter from when it originally formed, and that heat radiates outward, and it competes with sunlight. But there's a differential. There's more energy coming out than coming in, and that drives the atmosphere, and it creates all these amazing patterns that you see. You see the great red spot near the bottom there. It's a storm. It's about 2 to 3 times the size of the Earth. It's enormous, but it's temporary. It's been shrinking since we first saw it in the 70s, and in 20, 30 years, it will be completely gone. It's just a temporary feature. All these features are temporary. The stripes that you see across them, we call them bands and zones. They're different levels of atmosphere that we're seeing. Some are higher up, some are further down, and they all move in different directions because of all the turbulence in there. Jupiter, because it's so big, is kind of like a big vacuum cleaner. I mentioned a little bit earlier, but it sweeps up a lot of things, which contributes to why it has such a lot of mass. It's got about 60 moons that we've named. There's a lot of other moons that are smaller, and as we discover more, we tack on more to Jupiter's litany of satellites, but that's about 60 or so right now. Now, what's actually really interesting about Jupiter is that when we went out there in the with the Voyager missions, those were the first missions to seriously look at Jupiter. I mean, Jupiter was interested in everything. But the 4 Galilean satellites, these are the ones that were discovered by Galileo, they end up being fascinating when we got out there. They resemble terrestrial planets to a large extent, actually. Io on the left is the innermost planet. It's a world of it's like a world of fire. Every time we look at Io, there's 6, 7, 8 volcanoes erupting at any given time. And it's because Io is so close to Jupiter, the tides, which we talked about earlier in this class, the tides are extreme on Io. So extreme that the surface stretches and it melts the inside. And that creates all the volcanoes. So all the elaborate features that you see are all due to the volcanic activity that occurs. And just out from Io is Europa, which is a totally different world. It's a world of ice, not fire. And it's very smooth. It's covered completely in ice. And we think if you dig down deep enough, in some cases of several miles, that there's an ocean down there. Water, oxygenated water, actually. And we think there's anywhere in the solar system where life can reasonably exist, it would be down in that ocean in Europa. We've had several missions, several proposals for missions to go to Europa and drill through the ice and explore that ocean, but they've all been shot down at some point in their projects. So hopefully we'll make it there, but Europa is very interesting in that way. It's incredibly smooth, as I mentioned, because what happens is if the ice cracks, the water can well up, but then as soon as it gets to the surface, it freezes. It gets on the surface, it smooths out the surface, and it freezes. So over time, it just creates this incredibly smooth surface for Europa. In fact, if you scaled it down to the size of a ball, it'd feel like a billiard ball. It's how smooth it is. Ganymede and Callisto are big moons. Ganymede's bigger than Mercury, actually. So if Ganymede was out by itself in the solar system, we might call it a planet, actually. And we learned recently that Ganymede and Callisto have a ton of water in them, more water than the Earth does, including the oceans of the Earth. So that's very interesting. And there's a couple of videos I have down here. I'll put them in the description. They're just interesting videos taken from Voyager that looks at how the cloud motion and how Jupiter looked the first time we visited it. So, all right, Saturn. These pictures were taken with the Cassini spacecraft. Saturn was visited by Pioneer 11, Voyager 1, 2, and Cassini. That's all that's visited it. And Cassini is, I think, was recently decommissioned, actually. I don't think Cassini's around anymore. But Saturn, has this really elaborate ring system. The picture that you see in the bottom here is a picture taken from the other side of Saturn. This is with respect to the sun. So the sun is behind Saturn in this image. And so we get a nice silhouette of what the rings are like. So this is the most elaborate picture we have of the rings. And they're very thin. They look, the appearance of them, they look kind of thick, but they're actually very thin. They're 10 meters in thickness or something. It's very, very, very thin. And as I mentioned, they're most likely broken up pieces from a larger object. Something got close to Saturn. Saturn ripped it apart. And all those pieces over time just started orbiting Saturn and created this nice ring system. Saturn is even farther from the sun. Jupiter is around 5 AU. Saturn's almost double that. And it's even farther from the sun. So the gravitational influence of the sun is much weaker at Saturn. And that probably contributes to the fact that it has a huge satellite system. I mean, Saturn, as far as we know, has something around over 100 satellites, other moons. So very similar to Jupiter. In fact, you see that picture on the top there. I mean, you can see the band structure. Saturn's a very rapid rotator, and that kind of smooths out a lot of the features. So it doesn't have that sort of elaborate look. It doesn't have the same kind of turbulence. It's a little smaller, so it's lost some of its heat. So it doesn't look as elaborate as Jupiter does. One thing really interesting about Saturn, though, is it has a moon called Titan. And this is the moon. The picture in the upper right is how it generally looks in visual wavelengths. But the pictures in the bottom and the left here are pictures we've taken with an orbiter. So Cassini had a lander called Huygens. And Huygens was detached from Cassini and actually went through its atmosphere and landed on the ground. And there's a video at the bottom here, and I'll put a link in the description for you to look at that. It's a video of the descent through the atmosphere down to the surface. And Titan's amazing. It's the only moon in the solar system with a significant atmosphere. And when we descended down and we studied it, we notice that it has lakes and rivers, not of water, but of hydrocarbons, things that are like gasoline and things like that. The surface itself is super sticky. It's like Vaseline. It's like inches of it thick. It has wind, rain, thunder. So similar to the Earth in that way, but not a nice environment for humans at all. Now, the picture on the left here is sunlight that reflects off one of the seas of hydrocarbons that we see there. And, Titan, it's interesting because it's, the only reason it can have an atmosphere is because it's so far away from the sun. It's large enough and cold enough that can hold on to an atmosphere. Otherwise, it wouldn't be able to do that. So that's a very interesting one. But you should watch that video because it's neat to see the descent and look at all the scenery that's there. Okay, so the outer ones, Uranus. Now, Uranus is... Uranus is bland, right? It looks like milk of magnesia, if you know what that is. So yeah, Venus has a much blander appearance to it, and I'll get to that in a moment here. It has this milky, bluish looking atmosphere to it, mostly due to methane. We've only visited it one time. Voyager 2 visited it and took these pictures, and the atmosphere is bland for a good reason, though. Unlike Saturn and Jupiter, the internal heat source in Uranus is shut down. It doesn't have an internal heat source. And so what that means is sunlight hits Uranus, heats up the atmosphere, and there's nothing to really compete with that. So it just starts... What happens is the wind starts to pick up on Uranus. And the wind just goes and goes and goes. It just drives the atmosphere. In fact, we detected winds on Uranus and Neptune almost 1,000 miles an hour. And what it does is it just smooths out the surface completely. So we don't really have a lot of information about what's going on in there. We visited it once, way back in the this would have been like the late 80s by the time Voyager got out here. But yeah, we don't really know. It's possible that underneath that atmosphere is probably an ocean. Could be water, could be methane, could be other things. We think there could be significant ice chunks that float either in the atmosphere or in the ocean. We don't know. We really don't know, and we'd love to know. It's just not a high on the priority list of things to study in the solar system. So we won't really know. Maybe in our lifetime we won't even know what's going on with Uranus. But this is all the data we have, and there's a ring system that's kind of weak. It has around 20 or so satellites to it. Neptune's very similar. Again, visited once, bluish because of methane. It's got some more features on it. It's got we call the dark spot, the giant dark spot, similar to Jupiter's spot. It's a storm as well. But again, high winds, smooths out the surface. Probably some ice underneath all that stuff, but we'll never know. Interested in moons. Definitely interested in moons. But those are the outer ones. So I unfortunately don't have much to say about them because we don't know much about them. We visited them just once, and we probably never visit them again. So, all right. So which of the following is not a common characteristic of the Jovian planets? The answer here is C, rocky surfaces, right? None of those objects, you can't land on them, as far as we know. Maybe Uranus and Neptune, there's big chunks of ice that you could land on, but it's not obvious to us. But they have ring system, extended atmospheres, very large sizes to them. So, all right. So I mentioned a little bit about the ages. How do we know these ages? Well, it largely comes from something called radioactive dating, which is when we look at a sample of material. If that sample material is made of radioactive stuff, or maybe even part of radioactive stuff, we have a decent idea of how it decays. And the way radioactive dating typically works is we state it in terms of these things called half-lives. And so let's assume we have a chunk of radioactive material, and we know its half-life. What happens is that half-life, half of the material decays, half of it stays the same. And then after another half-life, another half of the radioactive material stays the same. So now it has 1/4 of its original radioactive material, and 3/4 is now changed. And then after a third half-life, you have another half of the radioactive stuff change. So now you have the original material is only 1/8 of the amount, and so on. And so if you have some decent idea of what you started off with, and you look at how much of it has changed, you may have a decent idea of of how many half-lives it's existed for. Okay. So as an example here, potassium-40 is a very common radioactive element. It's found everywhere. I mean, wherever you are right now, there's potassium-40 all over the place. It's in the walls, in the chair, and in the atmosphere, everywhere. It's not very harmful, so that's why it's not a problem. We know it has a half-life of 1.3 billion years. Part of the reason why it's not very harmful, it just has a huge half-life to it. Okay. But imagine we find a rock that contains 5 grams of potassium-40. Okay. Now, potassium-40 will decay into argon-40. That's the byproduct. So you find 5 grams of potassium-40. You realize that the rock, through other means, must have had 40 to begin with. Okay. And so now you want to figure out how old the rock is, right? Well, if you start off with 40, after one half-life, it would go down to 20. Another half-life would go down to 10, and another half-life would go down to 5. Okay. So there are apparently 3 half-lives that must have occurred to make the 40 go down to 5. We now have 5 grams of potassium-40, and the argon is now at 35 or so. So that means the answer here must be C. That's how old a rock must be if it's experienced about 3 half-lives. And that's kind of the technique we use. We don't just use potassium-40. There's a whole slew of elements that are used for this. And they all point to the same thing, that if we look at the Earth, if we look at other planets, if we look at asteroids, all the half-lives point to a very common age, and that age is 4.6 billion years old. And so that gives us, assurance that solar nebula theory is definitely the correct thing. All right. And that takes us to the end of chapter 7. We're going to be starting in on looking at other things in the solar system, space debris, and then we'll be talking about the sun soon. So see you next week.